DIY pulse oximeter. Circuit operation. I have developed DIY pulse oximeter that can be made with cheap and general parts and a 3D printer. In this video, I explain the circuit operation of this DIY pulse oximeter. I recommend that you watch general pulse oximeter principles in advance. Okay, let's get started. It's the DIY pulse oximeter schematic. PDF data can be downloaded from the web page. Necessary data to calculate SPO2 and heart rate is the transmission coefficient beta for red and IR. This circuit measures beta without an ADC by sweeping the LED current and measuring the time when comparator change. It's a simplified circuit of the LED drive circuit and the light detecting circuit. When LED select is high, the base of the transistor that drives the LED is at ground potential, so no LED current flows. When LED select is low, LED current relate to the output of the op amplifier. When charge is high, the charge on CT is discharged and VN goes to 0 volts. When charge switches from high to low, CT is charged with a time constant CTRT, so VN becomes the equation 1. Since this operational amplifier constitutes a voltage current conversion circuit, LED current is given by equation 2. The photocurrent of a phototransistor is proportional to the incoming light, which is proportional to the light transmitted through the finger, which is proportional to the brightness of the LED, which is proportional to the LED current. Therefore, the relationship between the LED current and the photocurrent of the phototransistor is given by equation 3. Where beta is the transmission coefficient which we need. A is a proportional constant that includes unknown values such as the light collection efficiency of the phototransistor and the luminous efficiency of the LED. The photocurrent of the phototransistor is converted into a voltage by RL and is compared with the Vref by an operational amplifier. The output of the comparator change when VDET equals Vref, so beta can be expressed as in equation 5. Where Tm is the time until opt goes high. As explained in general pulse oximeter principles, SPO2 can be calculated by the equation 6 from the maximum and minimum values of the transmission coefficient of red, 660 nanometers, and IR, 940 nanometers. In here, AC divided by DC was replaced using the maximum and minimum values of beta. In this equation, the proportional constant of beta including the unknown constant A is cancelled out, so R can be calculated from the measured value Tm and the time constant CTRT. In this way, SPO2 can be calculated by sweeping the LED current and measuring the time Tm when the comparator output changes. Go back to the actual circuit. In the actual circuit, the constants used in the simplified circuit are replaced as shown in equation 7. RL is parallel to RL1 and RL2, but RL1 is small enough compared to RL2, so it can be regarded as RL1. RLED is RRed1 when red LED, RIR1 when IR LED. LED select is the gate of Q2 for red LED and Q4 for IR LED. In the actual circuit, the phototransistor is connected to the NPN transistor as Darlington, and the photocurrent is multiplied by 1 plus HFE. This is included in the unknown constant A. To reduce noise, the amplified part of the phototransistor is embedded in the probe. As for the operational amplifier, I assumed an inexpensive single power supply type such as LM358. The common mode input voltage of LM358 is VCC-1.5 volts. I thought that the power supply of the signal handled by the operational amplifier should be made by a highly available 3.3 volt regulator, but the V-bus of USB will be 4.5 volts or less when the protection diode is installed. In this case, the common mode input voltage of the operational amplifier will be 3.3 V or less. Therefore, I adopted the method of reducing the power supply of the signal handled by the operational amplifier from VCC by the LED VF. Please note that this circuit is strongly affected by power supply noise. Stable measurement may not be possible if power is supplied from the bus-powered USB hub. Two types of PCB are available. PCB data can be downloaded from my web page. It can also be assembled with a universal board. Model a board does not have Arduino Nano block. Please wire them individually. I recommend if you want to design case yourself or use microcontroller which is not Arduino Nano. For the Model B board, I prepared the special case. For more information, please watch the video assembling controller. SW2 and BZ1 are optional. They have no functions assigned in the basic program. Finally, I will explain the adjustment of resistances. In order to keep the measurement time TM within the range of the program, it is necessary to adjust the resistance related to the brightness of LEDs and the light sensitivity. Resistors to adjust are RED1, RIR1, RD1, RL1. Derive the relationship between these resistances and TM. Solving equation 5 for TM we get equation 8. Here, since TM is a positive value, inside of log function will be equation 9. Expanding the log function of equation 8 by Maclaurin becomes equation 10. This is a graph showing the relationship between the order of equation 10 and the log function. This log function is monotonically decreasing within the allowable range, and the increasing-decreasing direction is the same as the first order line. What I would like to know now is the relationship between the increase-decrease in TM and resistance, so we can use the first order equation and TM can be expressed by equation 11. Here, since the change of beta with time is small, we can treat beta as a constant, and the relationship between TM and resistance is given by equation 12. Therefore, increasing RT1 increases TM for both red and infrared, and increasing RL1 decreases TM for both red and infrared. Also, increasing RRED1 increases the red TM, and increasing RIR1 increases the infrared TM. If the resistance value is not within the optimum range, the brightness of the LED during measurement will be dark and the ambient light noise will be large, or a large current will flow through the LED and the power supply noise will be large. Its initial values and adjustment ranges of them. Resistances adjustment is demonstrated in assembling controller. This is the circuit operation of this DIY pulse oximeter. For more information, please see the description of this video. Thank you for watching. I would be happy if you could share this video. Also, please like and subscribe.